Thank you very much. So I'm Klaas Wiersema. I'm going to talk a little bit about polarized light in optical transients in general. And this is work done in collaboration with many people, but I'm not going to read out the whole list. Let's see, how do I go? There we go. So I'll talk a little bit about how we do science of transient sources these days, and why polarimetry plays a role in that general perspective. I don't think I'll be saying anything new that you haven't heard before, but hopefully it will still be useful. And I'll talk a little bit about how we might be able to, in the future, add value to transient streams via polarimetry. Now, first of all, there's of course the usual debate about what is a transient and what is a variable. And now I don't want to get into that debate very much. But the obvious examples are things like novae, where there's clearly a binary before that is still there after the nova as well. Some people call that a transient, some people call that a variable. Well, I don't want to wade in that debate too much, but it is very clear that what is important is the physics that's in common between, say, extragalactic transients and galactic variable stars and sources like that, because ultimately it's the physics that matters. And I also want to highlight that, of course, the reverse approach, where you look through polarization data of, say, SFI and add a time domain component from transient surveys, is a really fruitful approach. Now, we all have seen that the transient ecosystem is changing very rapidly because new observatories are coming online. Of course, the one quite close and quite daunting is LSST. So that will boost our rate of detection massively of transient sources, going to the hundreds of thousands per night. And this is, it will also allow us to make good quality spectral energy distributions for a large number of them, because the sensitivity of radio and X-ray facilities is increasing as well. So this multi-wavelength perspective is becoming more important. And I think it's also fair to say that the attention is potentially shifting away a little from unusual single sources to the properties of large samples and getting our statistics proper for those. Now, multi-messenger astronomy is, of course, coming up, the ability to detect neutrinos and gravitational waves for sources. And similarly, what is also changing is the role of spectroscopy, particularly classification spectroscopy. In the olden days, when I started my PhD, you could still get a spectrum for almost every transient, but that's absolutely impossible now because the rate is so high. But this is, of course, going to change dramatically over the next few years as well. And that will probably result in a change in how we have to interpret our statistics that come out of our surveys. So that's something to think about. Now, with all those challenges come new software as well, new tools. So there are now really nice brokers, event handlers, and observation managers. There's abilities to do distributed observing, algorithmic observing. All those sort of things are becoming really commonplace these days and allow us to use proper techniques and data science techniques. So I think the key is a bit context, contextual surveys and contextual alerts, added value to streams, and availability of data and metadata. And of course, the key question is a little bit, what physics parameter space can we really optimize over in our new transient landscape and map that in a statistically sound way, in a way that we can model and that we can form priors for. A lot of that has to do with new techniques in data science that are coming into astronomy, like machine learning and so on, that allow us to ask more interesting statistical questions. So why do polarimetry then at all of these streams of sources? What's the point? Well, I think the key sort of summary, now I know I'm preaching to the choir here, is that polarization maps onto physics that is very poorly probed by light Gaussian spectra alone. It gives you a perspective you don't get from light Gaussian spectra. Now, just to give some examples of that, the obvious one is non-thermal emission in transient sources. We've already heard some really nice talks about jets in X-ray binaries, where that is a particularly clear example. Another one is here in the plot below. This is the spectral energy distribution of a gamma ray burst afterglow. You can see a very typical synchrotron spectrum in this source. Now, the polarization that we expect to see from non-thermal emission sources are generally dependent a bit on the geometry of the source, and the symmetry, the magnetic field properties, the order and the direction of the field, and of course the spectrum of the electron energy of the electrons that radiate. Another property that's of interest for polarization is shapes and geometry of sources. Now, one example is for example, supernovae. In the ejecta of supernovae, Thomson scattering takes place, that which polarizes the emission, and the polarization you receive depends on the geometry of the emitting area, scattering area. And the same is true for highly relativistic sources as well, like gamma ray bursts, where the polarization we receive is a direct function of the way that the R line of sight probes the shape of the jet. Now, dust, there's been a whole session about that, of course. Dust, not just in our own Milky Way, where it is potentially a bit of a nuisance, but also at the host galaxy of transients, where it is quite interesting, really. And the interest there, of course, is in understanding the dust properties better, so we might be able to do things better, like standardizing supernovae, but also to probe the near UV and far UV behavior of dust by looking at high redshift transients like gamma ray bursts. Multi-wavelength polarimetry is another thing I wanted to mention briefly here. It doesn't just end with optical, because we can do polarimetry now quite well, also at radio and at sub-millimeter wavelengths, even for fast TO, so even for objects where you only have a few hours to get your data. Now, an example is plotted here in the graph, where we got polarimetry with VLT and ALMA at exactly the same time of a gamma ray burst afterglow. And we see a higher polarization in the optical than we do in the submillimeter, which we believe is because there's a population of electrons in the shock that did not get accelerated, but does participate in Faraday effects and depolarizes the submillimeter emission that we see. Circular polarimetry has been mentioned before. There's not that much attention to circular polarization in transient sources, other than perhaps polars, of course. But gamma ray burst afterglows also show some circular polarization, as we found a few years ago. And it is really interesting to study that, because you get some really nice microphysics out of that. Now, back to the sort of the general picture. As you all know, there's different observables we can obtain for a transient. We can look at its flux as a function of time in different wavelengths. We look at the properties of the absorption and emission lines, at the high energy flux, perhaps the astrometry, the presence of neutrinos or gravitational waves, and polarization degree and angle is just one of those axes. And you can slice this multi-axis parameter space over different axes. You get plots like this that you see quite often. This is a plot of the typical variability timescale of transients versus their peak X-ray luminosity. And you can see here that sources where you have 1, 2, maybe 3 measurements cluster up into different regions in such a diagram. So that can help you classify a source, but it can also allows you to map out where the interesting physics may take place. Now you can take a different slice, like this down here. Here it's optical flux density versus radio flux density. And on the right-hand plot, you can see a collection of data points of various transients at various stages of their life, all plotted and clustering out into different regions in this plot. But any given source, of course, moves in this plot as a function of time. It walks, if you like, and that is shown on the left-hand plot, where for a number of sources, the walk in this diagram is indicated. So we can identify in a stream of transients, as long as we can combine different wavelengths there together, we can identify sources of interest by their location with respect to these big clusters, and by the direction and shape of their path in this diagram if we have more than one data set. So this helps us to identify what is interesting and what is not, and where to dedicate our follow-up time. Extended to even more dimensions, here's a nice X-ray binary outburst on the left, Maxi 1820 again, and on the right a peculiar supernova, 1820-18 Cal. And in both those sources, I plot the X-ray, radio, and optical brightness and the polarization, which is the size of the data point. There's a lot of interpolating going on, but the point here is that you can map what a source does quite well in these multidimensional planes and identify areas of particular astrophysical interest. So how could we do such a thing then in polarization space? So the plot on the left is one you've seen before, probably from the LSST handbook. So it's again characteristic timescale versus the absolute magnitude in the optical. You see this clustering of well-known sources of transients. And on the right, we made a similar sort of crude plot. It's not meant to be very accurate, where we show the degree of polarization on the left-hand axis, on the vertical axis, sorry. And again, we expect sources to cluster and to walk in this diagram as a function of time. Now, new surveys will produce really large numbers of transients, and robustly identifying which was of interest from an astrophysics perspective could be helped a lot by adding polarization information to that multi-parameter data set. So what we try to do is to do some classification polarimetry, where for a large number of transients randomly chosen, we obtain a snapshot of imaging polarimetry to see where they lie in this diagram. So what would we like to do? Well, spectropolarimetry would be great because you get a lot of information, but that's not realistic because most transients are way too faint to do that in a realistic way. Sensitivity is what we need, really. We need to go deep enough that we get out of the local group, also for faint sources, that we avoid cosmic variance issues and so on, and that we get down over the luminosity function properly. So we need to go down to magnitudes of around 20 or so to do this nicely. Now we need polarization of with reasonable statistical errors, so of order 0.1%, maybe as much as 0.33% or so. Reasonable systematic errors, of course. A reasonable filter range. There's no good using a filter in which your sources don't show up. We need access to field stars if at all possible, so we can calibrate for dust-induced polarization. And of course, we need a good sky overlap with the relevant feed surveys, such as ZTF or GOTO or Assassin or so on. And of course, ideally, we would like good weather and a robotic observing mode, so we don't lose sources to things that we can't statistically model so well. So there's a lot of wishes. And of course, we're not going to get all of those, but we can try. So first effort was that I did with my PhD students over the last few years. Was called Splot. It's a snapshot survey for polarized light in optical transients, and it does exactly what it says on the tin. We get completely randomized transient list in, where we obtain a single shot of imaging polarimetry in an optical band, usually V band, with the NTT, so 3.6 meter telescope. And then we map out this parameter space of time versus polarization, and we can combine that with radio and X-ray and so on. We got 5 nights of reasonable weather out of 10, and we got about 75 transients that we observed that way. They were randomly chosen, more or less. I'll get to that later. And a subset of them was observed twice or 3 times to check the effect of that has. And a small set of them got multiple bands as well, BVR or UBVRI, or in some cases RSZ. The resulting sample on the left, so that you can compare this plot with so on the left, you can see the resulting polarimetry that we got. Now you can see a lot of things in here. There's a couple of sources with very high polarization. Most of those are probably blazars, I suppose. Another thing to say is that at least half of these sources have no spectroscopic typing, so I don't know what they are. The only thing I know is that they're transient. You can also see that there's quite a lot of really bad upper limits of around 10–15%. That's not supposed to happen. This was because of really bad weather, big clouds coming over and so on. So in total, we got about 75 sources with reasonable polarimetry in this sample. We went down to about magnitude 20 or so, which takes about an hour on the NTT to get reasonable polarimetry for. Now we discussed all our source selection statistics in the paper written by my student. Now tricky things were clearly that the weather can really affect your statistics, because if the wind is from the north, for example, that was our problem, then you can only point towards the south, and then you're limited by very different feed surveys. You can't observe CTF sources, for example, but you have to observe Gaia sources or Assassin. Those have different cadences, different depths, and that affects your retrieval statistics of your that you want to get. So that was very hard. Another one is human bias. If you're faced with several sources that pop up at roughly equal priority, then which one are you going to choose? Often strange biases pop in there. Another difficulty is in predicting magnitudes at the time of observation. So if you have an alert from the night before, what is the magnitude going to be at the time that you want to observe? Sometimes you guess it very wrong, I can say. Now, we already found some very peculiar sources. We found some supernovae that are quite highly polarized very shortly after their explosion. So that was quite interesting. And there will be some papers on those in the future. We're now rolling this out a bit more via the Splot survey and the Pepper survey. What we try to do with Pepper in particular is to try to take the human out of the loop. So we try to move towards a fully robotic and algorithmic survey, which we focus on young transients, so transients that are less than a few days old, or in other words, sources where we respond within 24 hours to the alert, and where the last upper limit is within 3 days of the first detection. We use a robotic telescope to do this, the Liverpool telescope, and a robotic instrument called MOBTOP. Now, MOBTOP needs some introduction, I think. It's a dual camera, dual beam imaging polarimeter. It's a common use instrument for LT, where the two cameras of the polarimeter are tied to the wave plate, which rotates at a fixed speed of 8 seconds or 80 seconds. Those are the two settings. So that gives you 16 images per camera, or 32 in total, per rotation of the wave plate at steps of 22.5 degrees. So the systematic error is quite reasonable, about 0.1%, and the overhead is very small. It's very helpful. Now, we particularly use feed surveys that we can try to statistically understand a bit. In our case, that's ZTF and GO2. So those are sources where we can either get to the raw data and inject fake sources and understand the retrieval statistics properly, and sources where we can understand the cadence and the weather conditions very well. The sensitivity of MOBTOP and LT is reasonably matched. It's about 18.5 or brighter is what we pick for Pepper. Of course, ZTF goes down to 20.5 or so, but we are left with enough sources if you wish. And we completely Pythoned up the whole process of triggering. It all goes via a Python binding of RTML to the telescope. We use a filter on a broker to give us the list of sources to observe, and we use a TOM. It's the software made by LCOGT to analyze and contextualize our data. The Pepper interfaces directly to a big telescope program on VLT. In other words, Pepper feeds targets to VLT on short time scales. So if we see a young supernova with very high polarization, we can get VLT data hours later, which is quite helpful. Yeah. Now to move to the future, so some wish list for the near future, or the LSST era, if you like, where we're getting very, very many transients. It would be very nice if brokers and TOMs expand their capabilities more and homogenize, which is a bit of an issue. There's a lot of different standards. It would also be good to have a more homogeneous system of reporting and alerting, and a more standardized system, such as the VO events used to be in the olden days. ATELs and GCNs are not really fit for purpose anymore, in my view. We would also need new telescopes optimized for time domain studies, particularly polarimetry. Now, fortunately, NRT is one of those, the new robotic telescope. This is a 4-meter robotic telescope to be built on the island of La Palma. It's a follow-up of LT, and that's particularly built for time domain exploitation of LSST triggered alerts. And polarimetry will be a significant chunk of its activities, and transient polarimetry will be one of the public surveys it will do, most likely. Networks or distributed follow-up at multiple wavelengths, it's something that we're already doing a bit. It would be really nice to roll that out in a more formalized manner also for polarimetry. Of course, as we all know, polarimetric access to 4-meter and 8-meter class telescopes is not really increasing much. In fact, it is decreasing a fair bit over the last years. And in the infrared, that is a particular issue that we're seeing, at least for ESO countries. But there are opportunities now in that the ELT telescopes and their operation will force a rationalization of how 8-meter and 10-meter class telescopes are run and how they are instrumented. So that could be a good opportunity. Of course, the upgrade of Force 2 is particularly welcome in this respect. Now, easier multi-wavelength polarimetry would be very helpful. It was extremely difficult to get ALMA and VLT to point at the same source at the same time using the polarimetric mode. It would be really nice if you could extend it to way more wavelengths in a more less labor-intensive manner. And of course, there's always the the request for more theory, more models, and better simulations. I think I'll end there. Thank you.